Okay, hello everyone. Let us continue the second part of today's class. Okay. Okay, this is a framework. Okay, what framework? Okay, we need to see the previous page. Okay, all layers of the networking protocol stack. That is, these 5 layers is the framework with this cognitive engine. Okay. Okay, this is a framework that gracefully. Okay, what is gracefully? Please see the handout. Okay, page 11, problem 1. What is gracefully? Okay, solution. Moving in a smooth, relaxed, attractive way, or having a smooth, attractive shape. Okay. Let us go back to the slides. That gracefully allows cross-layer operations while retaining a modular architecture, and it will be used in this chapter when appropriate. Okay. Okay, why we all usually say the cross layer here? Okay, back to figure 2.1. Okay, because we consider 5 layers here, and our cognitive engine, okay, across these 5 layers on the input, on the output and the input. So we say this is a cross-layer operation. Okay. Okay, while retaining a modular architecture, and it will be used in this chapter when appropriate. As indicated, in this chapter we will focus on the use of ML, okay, that is machine learning, to perform distributed resource allocation. Okay, what is distributed resource allocation? Let us see the handout. Okay, problem 2. What is distributed resource allocation? Okay, solution. Distributed resource allocation, where a set of agents must assign their resources to a set of dynamic tasks, is a challenging, open problem in current multi-agent systems research. Okay, this is the distributed resource allocation. But in the wireless communication, what is resource? Okay, in the wireless communications, resources may include time, frequency, that is spectrum or frequency band, and space. Space means multiple antennas, and so on. And the power is another resource in the wireless communications. Okay, let us go back to the slides. Okay, in cognitive radio networks. Okay, we have introduced what is the cognitive radio in chapter 1. If you forget, please review the slides. Handout of chapter 1. Among the existing machine learning techniques, we are interested in those that reflect the cognition cycle and that are apt Okay, what is apt? Okay, let us see the handout. Okay, problem 3. What is apt? Solution: suitable or right for a particular situation. Okay, let us go back to the slides that are apt for their application in cross-layer solutions. Moreover, in adopting the CR paradigm, we are interested in considering machine learning techniques that do not presume. Okay, what is presume? Okay, let us see the handout. Okay, page 12, problem 1. What is presume? Solution: to believe something to be true because it is very likely, although you are not certain. Okay, let us go back to the slides. Do not presume an a priori model. Okay, what is a priori? Let us see the handout. Okay. Problem 2. What is a priori? Solution: relating to an argument that suggests the probable effects of a known cause, or using general principles to suggest likely effects. Okay, this is a priori. Okay, back to the slides. An a priori model for the effect of actions on the environment, but that derive this knowledge as part of the learning process in the CR, cognitive radio. An essential group of machine learning techniques that agree with these requirements is reinforcement learning. Okay, we have briefly explained what is the reinforcement learning. If you forget it, please review the handout of chapter 1. In a high-level view with reinforcement learning, an agent learns the best action to take by following a process of trying the different possible actions and evaluating their fitness with respect to achieving a goal. Okay, what is fitness? Okay, let us see the handouts. Oh, sorry. Okay. Good. Okay, problem 3. What is fitness? Okay, solution: how suitable someone or something is. Oops, okay, here is a problem here. Okay, I will fix this problem in the next version of this handout. Okay, let us go back to the slides. Okay, and evaluating their fitness with respect to achieving a goal. The competence. Okay, what is competence? Let us see the handouts. Okay, page 13. Okay, please wait me a minute. Okay, I need okay, where it is? I need to change the cursor. Okay, never mind. Oh, okay, this problem 1. What is competence? Solution: the ability to do something well. Okay. Okay. The competence of actions to achieve a goal is evaluated by calculating a reward or cost from the measured effect that each taken action has on the environment. The name reinforcement learning comes from the fact that an agent learns by trying out all actions multiple times, gradually favoring those that result in a larger reward, and eventually deciding on the action with the largest reward. Typically, the learning process gradually evolves from the exploration phase, where the agent tries actions mostly at random, with little knowledge of their effect on the environment, to the exploitation phase, where the agent prioritizes the trial of those actions with larger rewards. Okay, what is the meaning of this word? Okay, let us see the handout. Okay, page 14, problem 1. What is prioritize? Solution: to decide which of a group of things are the most important, so that you can deal with them first. Okay, let us go back to the slides. Okay, in chapter 1, we have discussed about the exploration and exploitation trade-off dilemma. Okay, if you forget, please review the handout of chapter 1. There are many reinforcement learning techniques. One of the most common is Q-learning, which is adopted in this chapter. Okay, what is Q-learning? Okay, please see the handout. Okay, problem 2. What is Q-learning? Okay, solution. Q-learning is a model-free reinforcement learning algorithm to learn the value of an action in a particular state. Okay, let us go back to the slides. Okay, one of the most common is Q-learning, which is adopted in this chapter. While reinforcement learning techniques provide the means for an agent to learn the effects of its actions on the environment, the process of trying the actions multiple times tends to result in a slow learning process. Okay, what does this word mean? Okay, what does means mean? Okay, the means here means approach, okay, or method. A recent development to address this issue, okay, what issue? Okay, that is the slow learning issue, has been to consider the effect of the action on the environment and its reflection on the intended goal as a function, with arguments being the taken action and the state of the environment. With the function being initially unknown, the agent learns it by applying machine learning techniques. Learning speed is increased by avoiding having to test all actions multiple times. This is the central idea of the deep Q-learning technique that is discussed later in this chapter. Okay, what is the deep Q-learning? Please see the handout. Okay, Page 15, problem 1. What is deep Q-learning? Okay, solution. In deep Q-learning, we use a neural network to approximate the Q-value function. Okay, we will explain what is the Q-value function in problem 2. The state is given as the input, and the Q-value of all possible actions is generated as the output. The comparison between Q-learning and deep Q-learning is wonderfully illustrated in figure 4. Okay, let us see figure 4. Okay, figure 4 shows the comparison between Q-learning and deep Q-learning. Okay. For the Q-learning, the inputs are state and action, and then we have a Q table. For the input state and action pair, we can check up in the Q table and find the corresponding value. The corresponding value is called the Q value. And what is the deep Q-learning? Okay, in deep Q-learning, the input is the state, and the state is input to a neural network, and the output of the neural network is Q-value action 1, Q-value action 2, etc. to Q-value action capital N. Okay, we assume that we have totally capital N actions here. Okay, let us go back to the slides. Okay, this is the central idea of the deep Q-learning technique that is discussed later in this chapter. Moreover, in the context of having cognitive agents that can communicate with each other, another approach to accelerate learning is to use the experience gained by some agents and transfer it to less experienced agents so that they can shorten their exploration phase. Later in this chapter, we will address this idea in more detail when discussing cooperative learning and transfer learning. Okay, the rest of this chapter is organized into 4 sections. Section 2.1 explains the use of Q-learning for cross-layer resource allocations, and Section 2.2 describes resource allocation based on the deep Q-learning technique. Section 2.3 focuses on how different CRs, that is, cognitive radios, can cooperate during the learning process. Finally, Section 2.4 presents some concluding remarks. Okay, we have finished the Section 2.0 introduction. Do you have any questions? Okay, if you do not have any questions, let us go to Section 2.1, Use of Q-learning for cross-layer resource allocation. Okay. For ease of exposition, we begin by considering a scenario consisting of a single primary channel where a group of SUs, that is, the second users, in the SN, that is, the secondary network, try to inject real-time subject to strict delay constraints. Okay, do you remember in the 5G communication, one of the features is the URLLC, ultra reliable and low latency communication. So the low latency means the strict delay constraints. Multimedia traffic, while avoiding interference to the primary transmission that exceeds a predetermined threshold. Without loss of generality, we consider that the channel is a quasi-static one, and that the single PU, that is, the primary user, transmits with fixed power. Okay, what is a quasi-static channel? That is, within a block of the time, the channel remains static. That is, the channel gain remains the same or unchanged. And between the different block of time, the channels is assumed as independent. Okay, or we need to or the channels are said to be independent of each other. Okay. In addition, the transmissions are subject to additive white Gaussian noise, AWGN, with power sigma square. Okay, I think the term additive white Gaussian noise, AWGN, is very fundamental in communications. So I do not tend to explain it here. Okay. Let P0 denote the PU's transmit power. Okay, let us see figure 2.1. Okay, P0 is the transmission power of the primary user. So now we know that this one is the primary user. Okay, back to the slides, page 20. And PI denote SUI's transmit power. Okay, where SU is the secondary. So back to the figure 2.1 again. Okay, if I remember correctly, it is on page 4. Okay, I am correct. Okay, so PI is the power of the I's secondary user. So we know that the CR, here means the secondary user, because CR means the cognitive radio. Okay, the secondary user needs the cognitive radio functions. And this is also the secondary user. Okay, so this is a SN link. Okay, secondary network link. This is also an SN link, the secondary network, a secondary network link. Okay, so let us go back to page 20. Okay, and PI denote secondary user I's transmit power, where 1 is smaller than or equal to I, and I is smaller than or equal to capital N. So we know that the capital N is the number of the secondary users, and there is only one primary user. Okay. Then the signal to interference plus noise ratio, SINR, of the PU, that is the primary user, is expected to satisfy the following condition. Gamma 0 P is the SINR of the primary user, is equal to G0P. What is G0P? G0P is the channel gain from the primary user to the primary. Okay, it is 25 minutes. Let us take a break.